Hi, this is David Bridges, and this is MEEN 3335, Intro to UAS, Unit 2, Lecture 3, Other UAS Platforms. And so, it's kind of with the previous lecture, what I'm going to talk about here is just some additional platforms to cover a broader array of the platforms themselves in terms of sizes and also applications. Some of the things we, for the most part, we've been talking about a lot of military applications, but I want to now expand the coverage to look at some non-military applications. But again, still, what we're primarily interested in is just getting a broad overview of unmanned aircraft platforms in terms of size, range, endurance, payload. Just get an idea of what's out there, how big it is, what kind of payload it can carry, and what it's doing. Okay. So again, this is another one I need to update. But the Technical Society for Aerospace Engineering is an organization called the American Institute of Aeronautics and Astronautics, AIAA. And they've stopped doing it most recently, but in the past they have done a annual UAV roundup in their monthly magazine. And so in July, August 2013, they did this roundup. They've done some since, so I need to update the information, but this just gives you the idea of what's going on. So 2013, the number of nations that were producing unmanned aircraft was 57. 57 different countries around the world were in the business of manufacturing unmanned aircraft. The number of manufacturers worldwide was 270. The number of different unmanned aircraft being built, just the different types, was 960, and it took 30 pages in the 2013 UAV roundup to cover all these. So it just gives you an idea of the scope of the industry. Okay. So we're just going to add some platforms to the ones we've already discussed, some military, and then some, in this case, civilian. Okay, now this is one that I think has both applications. This is an Austrian unmanned aircraft, the Schiebel Kammcopter S100. Has a heavy fuel engine option. So in addition to burning avgas, which is kind of the standard thing for piston engine aircraft, it can also burn some of the jet fuels. So JP5, Jet A, or JP8 jet fuels. These are heavier, they're kerosene based, okay? But it can burn those as well. As the typical payload we expect, EOIR camera. It has a payload capacity of 110 pounds, maximum takeoff weight of 441 pounds. The length is 10 feet, and the height is 3 feet 8 inches. You'll notice that basically those struts at the bottom are its landing gear. And in the bottom picture, there's an application. Actually, I think it has the possibility of firing a missile, I believe. So that was obviously a defense application. Max speed 138 miles an hour, range 112 miles, endurance 6 hours, so stay in the air a fairly long time, which is particularly good for a helicopter like that. And the service ceiling is 18,000 feet. Now, kind of on the other end of the helicopter spectrum, this is kind of the small unmanned aircraft, the quadcopters like the DJI Phantoms that we look at. So this is the Ariane Scout. It's a Canadian unmanned aircraft. EOIR, you can see in the picture there, basically the camera looking at you, the ball at the bottom of the aircraft. This one's controlled by a tablet PC interface, so basically a tablet or pad or whatever. Piloted by pointing to an area on the map. Height is controlled using a scroll on the touchscreen interface. So basically you have a map and you just put your finger on the spot on the map where you want the thing to fly to, and then over to the side there's a scroll bar and you move that up and down to adjust the altitude. And there are a number of other aircraft that do that as well today. See how big it is? It's basically it's about a little over 2 feet square, and each of the rotors is about 2 feet in diameter, about 1 foot tall. Loaded weight, so maximum Well, the loaded weight 3.1 pounds, maximum takeoff weight 3.74 pounds. So it's not heavy. LiPo battery. Okay, let me take that. The propeller diameter, each of the propeller diameters is a foot. The rotor diameter is basically 2 feet plus the separation between the propellers. So, yes, I messed that up a little bit. Max speed 31 miles an hour, cruise speed 40 kilometers per hour, range 2 miles. Okay, and that's more or less line of sight. Service ceiling 1,000 feet above ground level, presumably 15,000 feet above sea level, and can climb at a rate of 6 feet per second. Okay. Don't have endurance numbers there, but probably because it's battery operated, probably somewhere between a half an hour and an hour, if that much. Okay, on the other extreme, this was a Chinese unmanned aircraft known as a pterodactyl, excuse me, or the Wing Luong 1, which you see there on the side of the aircraft. Just showing this one because it looks very familiar to the Predator. Same general layout. You see the V-tail in the back, got the large nose at the front carrying the antenna, has the ball turret on the bottom with the sensors, EO and IR, carries a synthetic aperture radar. You look at the size, just under 30 feet long, just over 45-foot wingspan, gross weight 2,425 pounds, 3-bladed propeller to back. So you see the range, 2,485 miles, endurance 20 hours, service ceiling 16,000 feet. So these are numbers that are very similar to the Predator. You can see this one does carry munitions. So that's just a representative Chinese unmanned aircraft that looks an awful lot like an American unmanned aircraft. Okay, now this is the Heron. This was related to the Hunter, okay, but a more advanced version of it. A larger version, you see in the bottom photo how big this thing is. It's a very large unmanned aircraft. It's referred to as a MALE vehicle, medium altitude, long endurance vehicle. When we were looking at those high altitude unmanned aircraft in the other lecture, those are referred to as HALE, H-A-L-E, high altitude long endurance. Okay, this is a MALE, all right? So sensors, infrared, visible light, surveillance, standard camera system. You see the ball turret under the chin. Also communications intelligence, electronic intelligence, various radar systems. You see again the antenna mast on the nose, on the top of the fuselage, just behind the nose. Not one of the more attractive unmanned aircraft, in my personal opinion, but you know, and particularly because of that antenna mast or whatever it is. Now this thing could be flown in either a fully pre-programmed autonomous mode. You punch a button, takes off, flies, does a mission, comes back and lands, or manual real-time remote operation. So it could be under manual control the whole time, or a combination of both. Okay. What's impressive to me is that this thing does have a fully autonomous method of operation where it can literally on the ground, push a button, it takes off by itself, flies its mission, comes back and lands by itself. You see it's a pusher configuration, twin boom, horizontal stabilizer joining the booms at the back. Maximum takeoff weight 2,530 pounds, wingspan 54 feet. So max speed 130 miles an hour. Now the range number here I got was not the most accurate. It was given in the source for this, but if you look at how long it can stay in the air and so forth, and the speed, the more likely range estimate's about 1,860 miles. Okay. Endurance 52 hours. Okay, so it'll stay in the air a long time. Payload 550 pounds, so fairly heavy payload. Okay, now the replacement for the Heron was the I-10. again, another Israeli product. You see a picture of it here. It's even bigger. Now it has a maximum takeoff weight of 10,250 pounds, 4,400 pound payload. This thing can carry a lot. Wingspan 86 feet, length 43 feet. Now it's a Pratt & Whitney turboprop, the PT6A, which is actually a very, very common turboprop engine used on a lot of aircraft. Max speed, and I don't have the number there for miles per hour. Range 4,600 miles, endurance 70 hours. Okay, this thing can carry a big load. It can carry it a long time to a great distance. Well, now let's go to the other end, and we're back to battlefield reconnaissance. And again, these are what I'm going to show now. This one I'm including because it's a fairly common battlefield reconnaissance aircraft, and also it shows a geometry or configuration that unmanned aircraft are tending to move toward now to some extent. So you notice that it's basically this long stick that's the fuselage, and the engine is a motor at the front end of the stick. So that cylinder at the front is basically the motor. The propeller is attached to the end of that, and then the payload is in this thing, the term for it, basically the cylinder underneath, and that actually carries the payload. Again, battlefield reconnaissance is going to have a EO/IR camera on it, backpackable, as a crew of 1 or 2 to operate it, electric propulsion. Now this one has an airborne airbag system for point recovery. I believe it pops a chute and puts out an airbag at the bottom and just comes in for landing like that. So that's how it's recovered. Takeoff weight 16 pounds, so it's not very heavy. Max payload 2.4 pounds, kind of big, almost 10-foot wingspan. Stay in the air 3 hours. Now that's good for electric propulsion. Being able to stay airborne for 3 hours. Service ceiling, supposedly 15,000 feet. Range anywhere from 12.5 to 25 miles. Don't have a speed here, but basically the range is likely radio limit. But again, I wanted to include this one in particular because there are a number of unmanned aircraft being built now that have this configuration, including the Skylark 2, which is the upgrade of the Skylark 1. Now this one requires a catapult launch, but still has the airbag landing. So you can't just hand launch it. It has to be launched with a catapult, but then it can be landed with parachute and an airbag. It has the a multiple sensor payload, video camera, and a forward-looking infrared camera, also with a laser with auto tracking capability. So a number of additional things in the payload, which is in this pod underneath the fuselage. Again, you notice closely here, the electric motor which pulls this thing is basically on that stick that's the fuselage. It's kind of a minimalist unmanned aircraft. But now it's considerably heavier. It's 143 pounds, so you're not just going to toss it. It's almost 10 times the weight of the Skylark 1. Payload weight 20 pounds, so now that pod underneath can carry more stuff. Wingspan 21 feet, endurance 4 hours. And again, it's electric propulsion, so 4 hours endurance, that's very good. Likely the pod underneath has some additional batteries. Range 38 miles. Okay, another coming to be common battlefield reconnaissance UAV is the Silver Fox. Now initially developed by the Navy so they could fly it around and spot whales and other sea mammals in the operating areas. They're about to begin an exercise and they don't want to run into a whale or anything. They would use these to fly over and spot them. Then they got a request from the Marine Corps for tactical reconnaissance, intelligence, surveillance, and target acquisition unmanned aircraft for small units. Okay, so they developed this thing. The guy who was the external pilot for some of our RS-16 exercises. Actually spent, I think, 9 months either in Iraq or Afghanistan. I think he was in Iraq, but I'm not sure about that. But he was over there for about 9 months flying these things. Okay? And he was also in charge of maintenance. And so you see the operations. It has this compressed air launcher, which basically can be set on top of the case, which carries, there's one case for the launcher, another case for the aircraft, and this launcher thing can basically be set on top of the cases. And so there's the launcher. It has a cylindrical fuselage with a kind of rounded nose. To me, the kind of the characteristic feature of the pistons sticking out of the nose. You kind of see it. You can kind of see it in both photos. To me, that's just kind of a distinguishing feature. One-cylinder engine. Okay, so it's 8 piston. Has a length of 4 feet 10 inches, wingspan 7 feet 10 inches, max weight 26 pounds, payload weight 4 pounds, max speed 63 miles an hour, endurance 10 hours, so it can stay in the air for a while, and then range 20 nautical miles. Here specifically stated that it's determined by the line of sight data link, the radio link and the communications link for the payload. All right, another relatively small unmanned aircraft. This is the in situ aerosonde. That's kind of an interesting corporate history. It was first developed by in situ, which is a company now owned by Boeing. It was built in Australia by Aerosonde Limited, which was acquired by AAI, which was then acquired by Textron. So developed as the in situ aerosonde, was being built by, I think what happened was Boeing bought in situ, spun off the Aerosonde to this company to build, Aerosonde Limited. That company got bought out by another company, which got bought out by another company. So anyway, it was designed to collect weather data. So this is not just the standard EOIR payload, but it was designed to basically fly over oceans, other areas, and collect temperature, atmospheric pressure, humidity, wind measurements over oceans and remote areas. Okay? So multiple sensors on board, not just cameras. They would do polar survey missions. They use a digital camera, an infrared thermometer, air pressure, temperature, humidity sensors. Okay, so these are all, this thing was built to basically make atmospheric measurements. Okay, it was actually built as a scientific unmanned aircraft to make atmospheric measurements. And it was the first unmanned aircraft to cross the Atlantic Ocean. That was launched from somewhere along the northeast coast, maybe somewhere in Canada, and then I think it landed in Ireland or something like that. So it wasn't like a New York to Paris kind of thing, like a Lindbergh thing, but it did fly over the ocean. I talked to the manufacturer of this thing, the representative of the manufacturer of this thing, when I was at a meeting in Scotland about unmanned aircraft, and I believe he said there was a satellite link that they talked to it on, but I'm not completely sure about that now. We did talk about this particular mission, but it's been a while. But anyway, so it was launched, and then they kept in touch with it somehow, and then they recovered it on the other side. Not huge. Length is 5 feet 8 inches. Wingspan 9 feet 8 inches. Height 2 feet. Loaded weight 28.9 pounds. Modified R-120 model aircraft engine, so it's a piston engine, and you can see that in the bottom photo there. Very kind of lightweight, minimalist construction. You've got the fuselage. You've got the booms, which just kind of stick out from underneath the wings, and then there's this inverted V-tail which connects the booms. So you have combined vertical stabilizer and horizontal stabilizer in this V-tail, and also the fact that they're connected gives it structural rigidity. Okay, so you'll see that in others, like the Shadow. It's kind of the same way. But this is a fairly significant vehicle. Okay, now this is one of the early U.S., well, one of the early unmanned aircraft operated by the U.S., AAI RQ-2 Pioneer, which is an upgrade of the Mastiff that we've discussed before. The Mastiff was one of the first, twin boom pusher configuration unmanned aircraft. Well, this was basically essentially one of the first to go into operation in the U.S. military, and actually it was initially developed for naval use. They wanted to mount these on battleships to provide gunnery spotting. Basically, you've got battleships, you're firing these massive cannon that can send shells 20 miles downrange. Well, you want to be able to go out there and look and see where they're landing. So that's kind of the purpose of this thing, which is why it was a rocket-assisted takeoff aircraft. You see that happening here in the picture. Basically, it's a zero-length launch. Did not require a runway. Can be launched directly from a ship, and I have seen photos of that happening. You can probably dig them up on the internet. Now, eventually, this led to other aircraft, in particular, finally, led either directly or indirectly to the Shadow. But it was in service for a while. Again, you see the ball turret underneath, which had the EOIR sensor, relayed analog video in real time, so people watching basically watching the TVs on the ship to see what was going on. Length of 14 feet, wingspan of 16.9 feet, speed 110 knots, range 5 hours, at 100 nautical miles, so basically could go out, 100 miles, stay there for 5 hours, come back, ceiling 15,000 feet. Now, I don't have it here, but there's also a photo. There's one of these hanging in the Smithsonian Institution. So an example of an unmanned aircraft that's hanging in the Smithsonian is one of these. And it basically is there as kind of the predecessor of a lot of the other unmanned aircraft that are currently in use in the military. Okay, now this is a Czech unmanned aircraft. This is a smaller aircraft, as you can see there in the picture. It's a target drone, so we're back to that. But it's a smaller drone. It's a higher speed drone. The speed is 244 miles an hour. Okay, so it's designed to be high speed, harder to hit. So for target practice. And there's a rail launch. You don't see the complete rail. You see the carriage it sits on when it launches. But so there's basically something that accelerates it along the rail and then it launches. Wingspan of 6 feet. So it's a little bit bigger. It's kind of hard to see the picture, but actually a little bit bigger maybe than I suggested. Length 4.5 feet. Height 1.8 feet. It's the belly lander. There's no gear on it. 47.3 pound maximum takeoff weight. Again, we said speed 244 miles an hour. Nothing here about endurance. Not supposed to be flying a long time. It's a target. Fly up to 10,000 feet and has a operating range of 18 miles. Okay, and we talked about the Scan Eagle in a previous lecture. Well, this is what's supposed to come after the Scan Eagle, the RQ-21 Blackjack, and notice it's an in situ product, which is now a Boeing product. But again, it's supposed to replace the Scan Eagle. Same type of recovery system, the Skyhook system, so it snags a hook on the end of one wing and brings it down, as you see in the bottom right-hand picture. It is bigger than the Scan Eagle, about twice as heavy. Maximum takeoff weight is 135 pounds. Now, one of the main configuration differences is, if you remember the Scan Eagle, it was just the fuselage and the main wing. It was basically a flying wing. The main wing was more swept. The wings went back a little bit more, but that was it. On this aircraft, you see they've added the twin booms, the twin vertical stabilizers to the back, and then the vertical stabilizers connected by horizontal stabilizer at the top. So that boom rear control surface assembly was added, relative to what the Scan Eagle looked like. Probably to address some stability and control issues. That would be my guess. So, like I say, it's about, I think the Scan Eagle is maximum takeoff weight in the range of 60-something pounds, and this is about twice that. Wingspan is bigger, 16 feet. Max speed 104 miles an hour. Cruise speed 63 miles an hour. Endurance 24 hours. It stay in the air for a while. Service ceiling 19,500 feet. Okay. Now, this is the big brother to the RS-16. Now, Arcturus is the company that made the RS-16 platform that American Aerospace then took and did some modifications and sold to us. Well, this is the T-20. Okay. Now, this is the one. So it's also a belly lander. It's basically the same configuration, same kind of geometry as the RS-16. It's just bigger. Okay. And so you see in particular the ball turret sticking out of the belly. Okay, that's the way that the Arcturus line normally works. But it is a belly lander, so you really hope that retraction mechanism works when you get ready to land this thing, or you just had a really bad day. So again, an EOIR camera on this independently pointable, targetable ball turret sticking out of the bottom. This was the first unmanned aircraft to see and avoid a general aviation manned aircraft using an ADS-B transponder. We'll talk more about that later. The ADS-B transponder is the technology that's going to replace the existing transponders, and it allows aircraft basically to talk to each other. We'll talk, like I said, we'll talk more about that later. But this one had it mounted on it, and they did a test, and it's flying along. General aviation aircraft flies, a manned aircraft flies presumably an intersecting flight path. And so this thing was able to detect it and then figure out, okay, I need to go some way to avoid collision. And so that's what happened. Now in August 2013, they flew one of these to an altitude of 23,500 feet with no special modifications. That's pretty good altitude for something that doesn't have a turbocharger or anything like that. Like I say, it is bigger than the RS-16. Wingspan is 17.2 feet. The RS-16 is just under 13 feet. The empty weight is 110 pounds. The gross weight, maximum gross takeoff weight is 775 pounds. The RS-16 is, I think, 85 pounds. It's about twice the weight. It has this 4-stroke piston engine in it. Back speed 104 miles per hour. Range 55 line of sight miles. So you still have to be able to see it via radio, but if you have an amplifier on your transmitter and an amplifier on the aircraft, you can, if you're willing to go the trouble of getting a license from the Federal Communications Commission, you can up the power, therefore up the radio range, and that's what they've done here. Endurance 16 hours, service ceiling 15,000 feet. And you see it there on the piston launcher like the one we have, except it's a bigger launcher, a heavier launcher, because obviously the thing is weighs about twice as much as the RS-16. Okay, now this one is, well, we don't know a whole lot about it. This is the RQ-170 Sentinel. It's presumably a secret aircraft. Now, probably what we know about this thing is from the fact that one was brought down by the Iranians in December of 2011, okay, and intact, roughly intact. Now, it's either there was either a system failure or there is some suspicion that it was spoofed, that basically the Iranians somehow managed to take over control of the aircraft while it was flying and force it to land. Then they came out with one very similar to it. I'm not sure how well it's flown, but anyway, I think basically that's how we know what it looks like, pretty much. This is actually an image produced by someone who's building models of these things, computer-generated image. So these are all estimated. It has a turbofan engine. Don't know how fast. Probably flies up to 50,000 feet. We just know they're there. We don't know exactly what all they can do. Someday we probably will, not yet. So, but we know they're there, okay, because one did get brought down, and so we know about it. Okay, but that's kind of the opposite extreme end of unmanned aircraft. Now, a different application, a non-military application. One of the things that unmanned aircraft are being used a lot for these days is surveying, aerial surveying. Because you can take these things with the GPS information we have, with the camera capabilities, with the ability to precisely locate points on the ground in terms of the, in relation to the images that we acquire of those points on the ground. These things are becoming very valuable for surveying, okay? And so what this thing does, this is a Polish unmanned aircraft, Terex, delivering data for generating digital elevation model using external photogrammetric, always have trouble pronouncing it, photogrammetric software and orthorectification procedure, data for precision agriculture, obtaining service maps using mosaicing software. So kind of what we do with the RS-16, but a lot more accurate. Okay? It has this kind of unusual configuration. Basically, you have the fuselage with this pylon on the top, and then the wing sits on top of the pylon, and the motor's up there. Electric motor, 9-foot wingspan, 1 foot height, max takeoff weight 11 pounds, so they're not heavy. Can stay in the air 55 minutes with about a 2-pound payload. If it has a lighter payload, you can put more batteries on it and stay in the air for 2 hours. Okay, cruise speed 75 miles an hour. And you see that service ceilings, but you don't necessarily want to be flying high when you're doing surveying. So the cruise altitude is typically 300 to 1,700 feet, depending on how the resolution you want the photo. Remember, the R16 at 1,000 feet, the resolution for each pixel is 2 inches on the ground. Okay, so if you need higher resolution, you fly lower. Okay, so you might be able to fly at almost 10,000 feet or whatever, but you don't necessarily want to if you're doing survey work. Okay, so that's the purpose of this aircraft. And one basically doing the same thing is the Aerohawk, which is manufactured in New Zealand. Looks a lot similar to the Puma, actually. But same thing, it's surveying, basically taking a photograph and turning it into a high-resolution map. Okay, Google Maps, they do this kind of thing. Okay, now this one basically has just a Sony camera in it, a very high-resolution camera, a 16-megapixel camera with a 15-millimeter ultra-wide survey lens. So a lot of these payloads, you'll see them, and they'll basically be some kind of metal frame, and it will just have a digital camera like you would buy at Target or Best Buy and go out and take pictures with, where that same camera body with a similar lens is just sitting there, such that it's pointing down out of the belly of the aircraft. So you see, it's fairly light, 12 pounds, hand launched, electric motor, staying there an hour to hour and a half, 37 miles an hour. So again, another surveying application. And a third surveying application is the SenseFly EB. You see the picture there, that's actually Dr. Michael Sterick. He's a professor in GIS here on campus, does a lot of surveying work and research into how you go about doing surveying work with things like this. And this is a very popular surveying platform. Again, a 16-megapixel camera, electronically integrated control. The thing about these is that they have that and they have differential GPS. So, very precisely the location of the airplane, because you have differential GPS and an onboard INS system, so you know the orientation of the airplane. So with all these things, you can get a very accurate mapping of the point on the ground. When you take a picture and you figure out, okay, in that picture, this point is on the ground at a certain place, you need to compare it with where that point actually was, it's very close. Sometimes it's on the order of millimeters, the error. So it's very, very highly accurate. He has used this to actually make maps over campus and has mapped other places as well. But you see how big it is. So it's light. It's only about 1.5 pounds takeoff weight, 3-foot wingspan, staying there 45 minutes, up to 1.9 miles with a radio link. So that's again, that's a example of a excuse me, fairly common surveying platform. Then last one we'll look at in this lecture, way at the other end, this is the Northrop Grumman X-47B. This is known as a UCAV, an unmanned combat aerial vehicle. Okay, some of the thinking is that at some point, fighters that fly in the air are not going to have pilots in them. They're going to be unmanned. They're going to engage in dogfights or do whatever without a pilot on board. Okay, so this is one of those aircraft. Notice it looks not too different from the Sentinel, which was a Lockheed product, but typically the mission will drive the configuration to a particular design. So it's not uncommon to see multiple configurations that look a lot the same if they're doing the same thing. Now, this one was designed to be flown from a ship, and so these photos are from basically, you got to test it. You got to, see if you can take off and land from ships. Well, what they did first was that, I believe what they did first was launch it from the ship and land it on land. So they manually loaded one, used a crane or whatever, put it on the ship, took it out to sea, launched it using the catapult system on the ship, and then landed it somewhere on the land. Then the next test was to launch it from the land and land it on the ship, so using the hook system, the tail hook and all that to retrieve it. And then the final test was to launch it from the ship and then recover it on the ship. And they managed to do all of that in 2013. So you see how big it is. Length is 38 feet. Wingspan is 62 feet. Okay, so it's fairly big. Empty weight, 14,000 pounds. Maximum takeoff weight, 44,000 pounds. This thing can carry munitions. That's why it has such a difference between empty weight and maximum takeoff weight, because it's designed to carry bombs, missiles, that kind of thing. Has a turbofan engine in it. Max speed just subsonic. That's all we know. Cruise speed Mach 0.9 plus, high subsonic. So it's designed to fly fast, but it's not a supersonic UAV. Range more than 2,100 nautical miles. Service ceiling 40,000 feet. Okay. So you see the weapon bays providing for up to 4,500 pounds of ordnance. That may be each. And then you look at the fuel weight. So that if you're going to fly 2,100 nautical miles, you're going to carry a lot of fuel. If you're flying on a single turbofan engine, you're going to have a lot of fuel on board to go that far. So by the time you add the fuel and the munitions, you go from the empty weight of 14,000 pounds to the maximum takeoff weight of almost 45,000 pounds. Big, heavy unmanned aircraft, and it works. They have launched it from the ship. They've landed on the ship. They've also done air-to-air refueling of these things. Don't have that here, but you can find pictures of it on the web. But they've actually done that also. So now it's just a question of programming it to do the other things they want to do. That's where they're still working. But the basic platform itself is operational, or has done what it's supposed to do. Okay, well that concludes this lecture. What we will get into, and this also concludes the unit. So the next unit, we will start looking at some of the technologies within unmanned aircraft. I believe the next topic is actually controls. So we're going to start looking at what it takes to actually control these things. We're going to get down kind of at the guts of the aircraft. So I'll conclude the lecture now, and we'll pick that up with the next lecture.